Last time we related strains to curvatures for symmetric laminate that was subjected to pure bending. And so in this video we're going to develop the bending stiffness matrix that will allow us to look at the applied moments and relate those to the curvatures. So to start with, let's consider the stress distribution on this little 1-inch wide piece of the plate. And because of the fact when we put a moment on this that it is symmetric, it means that the midplane is location of the neutral axis. So any stresses above are going to be compressive, and any stresses below the midplane are going to be tensile for our definition of what a positive in m sub x is. So I've kind of drawn those. Now, of course, they can vary. Well, we know that if this was an isotropic material, they would vary from top to bottom, but with the different stiffnesses of the layers, it could vary even more than that for the composite. But really the definition of the moment resultant, m sub x, is that it is the resultant of these stresses in the x direction. So with that in mind, before we can really do the numerical part of this, we have to establish a numbering convention here. Now, we didn't need to do this when we just had in-plane loading if we were symmetric, because it didn't matter where each layer was relative to the midplane. It just depended on its thickness as long as the laminate was symmetric. But now it does matter where every layer is, just like you learned in mechanics and materials. When you were looking at simple beam theory, you know that the further you are away from the neutral axis, the higher the moment of inertia due to the parallel axis theorem. Well, a similar kind of thing works here for the composite layers. The ones that are further from the midplane or the neutral axis are going to have a greater impact on the bending stiffness. So anyway, we start at the top. Layer number 1 will be the top layer, and capital N will be the number of layers. So we've just identified an arbitrary layer as layer K. Now we need to know the interfaces between all these layers. In other words, what's the top and the bottom surface of each layer. So we'll start at the top with Z sub 0 and then start numbering from there. So when we get down to the kth layer, its top surface will be Z k minus 1, and its bottom surface will be Z of k, and down to the bottom layer where the bottom surface is going to be Z sub n, and its top surface is going to be Z of n minus 1. So we have n layers, which means that we had to start at 0 so that we have n plus 1 interfaces, including the top and the bottom. Now keep in mind we're always measuring Z positive below the midplane. Alright, so going back to our little stress distribution and looking just at a very small cross-sectional area d sub a. Now, this is on a 1-inch width. Remember that the moment is going to be in units per unit width. And so let's look at the total force that's acting on that little area. It's going to be the stress times the area. And so the moment about the neutral axis would be that force times the distance z, or z times sigma x dA. Now, of course, the total moment is going to be when we look at the effects of all of the little small areas. In other words, when we integrate that over the entire cross-section. So we integrate z sigma x dA. But remember dA here, in this case, because we have a 1-inch width, the area is just 1 times the incremental thickness, dz. And so we can write the moment equation like this. We're integrating now over the z-coordinate from the top to the bottom surface. Now, of course, you have to remember that the layers are probably going to be have different stiffnesses, and so we need to break up that integral and also show it as a summation here. So we're going to sum over our total number of layers the integral z sigma x dz. And so for each layer, we're integrating it from its top surface to its bottom surface. In other words, zk minus 1 to z sub k. And similarly, We have similar equations for m sub y and m sub xy. M sub I based on the stresses in the y direction, normal stresses in y direction sigma y, and m sub xy based on the shear stress tau sub xy. And so we can put all those together in this matrix form here. So the k superscript, remember, is just for the kth layer. So for each layer, we're doing the integral of the stress times z dz, and then we're summing those up over the number of layers. Now, of course, we can now use our stress-strain equations we came up with in a couple of sections ago. The sigmas are the q-bar matrix times the strains. And so we're just replacing here the stresses with the q-bar stiffness matrix times the strains. Now remember, the q-bar matrix is not going to vary across the layer, so we can move it outside the integral. But still, well, we'll do that in just a moment, sorry. But we're going to replace epsilon x, epsilon y, and gamma xy with the expressions we came up with in the last video, z times the curvatures, z times kappa x, kappa y, and kappa xy. And now the next step is we'll recognize that this is constant within the layer, so again we can move it outside of the integral. We'll also see we've got a z here and a z there, so that'll make a z squared. And so here's our result, is that we have moments on the left side, we have the curvatures on the right side, and relating them, now we have the bending stiffness matrix D. And so in shorthand here, the moments are related to the curvatures by the D matrix, but of course we usually know the moment resultants as the beginning of the problem, so we take the inverted D matrix, multiply by the applied moments, and come up with the curvatures. And of course, once we know the curvatures, we can look in at each layer and find what the stresses are, what the strains are, and then the stresses with the equations we've already developed. So if we look at the D matrix, if we evaluate that integral, z squared dz, then we can enter it like this: 1/3 z of k cubed minus z of k minus 1 cubed. Remember, z of k would be the bottom surface of the layer. It's distance below the neutral axis. And z of k minus 1 would be the coordinate of the top layer. And remember, we're always measuring z from the midplane downward. We'll see an example of that in the next video. So if you think about what we did in mechanics and materials, I mentioned that the further a layer is away from the neutral axis, the higher its stiffness is. And so if you remember in mechanics and materials, you looked at the moment being EI times the second derivative of the displacement. And we also said the second derivative of placement is, for small deformations can be related to the curvature. But you might think that the moment of inertia I might be similar to the expression 1/3 z of k cubed minus z of k minus 1 cubed. And in fact, it is the moment of inertia of a 1-inch wide segment based on how far it is away from the neutral axis. Now, I do show the proof of this at the end of the course pack material. It gets a little not complicated, but gets a little messy with the algebra, so rather than present it here, if you're interested in that, that is at the end of the course pack section. Okay, so we have everything we need now to be able to evaluate a laminate, symmetric laminate that's subjected to bending, and we'll do that in the next video.